So, students, as per syllabus, this is your syllabus for X-ray diffraction technique as it is. So, first part is fundamentals, in which there is origin of X-ray. Then we are supposed to study Bragg's law and its mathematical derivation. Then there is Bravis Lattices and Miller indices. Now, this part is not there in the syllabus of MPharm. Then there is pharmaceutical application part, crystal structure determination and polymorphism determination. Then there is instrumentation and working principle of those instrument parts. First is X-ray source. In X-ray source, you have only one of the source, that is X-ray tube source. There are four ways of generating X-rays. We have only one in your syllabus. Then is X-ray monochromators. There are two types of monochromators in X-ray. We are going to study that. And last is detector. In detector, we will see that the detectors we have just seen in previous lecture. Radio pharmaceuticals में हमने दो detectors देखा था. These are the same detectors used here in X-ray diffraction technique. Okay. The sequence is not usual sequence given in your syllabus. Usually it is like we first study principle, then we study instrumentation, and then last is application. Okay, यहाँ पे fundamentals के बाद सीधा application पे आए हैं, then they have gone for instrumentation. But we will see the best way possible to go about this chapter. Okay, so to begin with basics, discovery of X-ray. A German professor in 1895 named Röntgen discovered this X-ray. He was working with electron discharge tubes. Okay, and near to this electron discharge tube, there was one screen placed. That screen was coated with barium platinocyanide. When those electrons may have escaped his discharge tube and bombarded on the screen, the plate, that screen started glowing. Now, but the direction of the electron and the placement of this screen, it was like at 90 degrees perpendicular. So it was definitely not electrons that are bombarding on the screen. So the professor did not know about these rays, these electromagnetic rays. So he called them as X-rays. What are X-rays basically? On the spectrum of electromagnetic radiation, you can see their position. They are situated between UV and gamma rays. So X-ray are invisible, highly penetrating electromagnetic radiation of much shorter wavelength. When wavelength is shorter, we say that energy is higher. So energy is higher and frequency is also higher. Now, as compared to the visible light, the wavelength range for X-rays is from 10 raised to minus 8 meters to about 10 raised to minus 11 meters. The corresponding frequency range is about 3 raised to 16 to about 3 raised to 19 hertz. Now, what are general properties of X-rays? Now, remember, these X-rays are electromagnetic radiations. So, all the properties of electromagnetic radiation will be applicable to X-rays. There are few exceptions. We will see those exceptions. They are electromagnetic radiations of very small wavelength. They travel with velocity of light, that is 3 into 10 raised to minus 8 meters, 3 into 10 raised to 8 meters per second. It should not be minus, it should be raised to 8. They affect photographic plates. They are not deflected by magnetic or electric field, therefore do not possess any charge. Now, generally electromagnetic radiations are affected by magnetic fields and electric fields, okay, because they are electromagnetic radiation themselves. But because of high energy associated with these electromagnetic radiation, they become unaffected. उनका energy इतना ज़्यादा होता है that magnetic field and electric field do not pose any deflection in their path. But when they pass through gases, they ionize the gas through which they pass. They are highly penetrating and can pass through many types of solids which are opaque to visible light. For example, wood, paper, cardboard. Now that was properties of X-ray, but how X-rays are originating? So X-rays originate from atoms, or more specifically, it is not nuclear related phenomena, it is the electrons related phenomena. So atoms in general consist of nucleus and electrons. If you talk about electrons, the innermost orbit is K, then next to K is L, M, and N, and so on. except k orbital, they all possess k, l, m, n. They all possess subshells. Now, to detach electron from innermost orbit, maximum energy is required. So, the electrons which, when detached from innermost orbits k or l, they, when they detach from the nucleus, they emit X-rays. Now, there are many ways of generating X-rays. As I said in the beginning, you have only one in your syllabus, that is the X-ray tube. X-ray can be produced in a highly evacuated glass bulb called X-ray tube. So this over here you can see X-ray tube. This is the bulb which is evacuated. This evacuated bulb is attached to, or it contains, two electrodes, cathode and anode. This anode is generally made up of platinum, tungsten, or any other heavy metal of high melting point. The point to be noted is it should have high melting point. And then you have a cathode. This cathode is mostly tungsten filament. You can see the filament over here. Okay. Now, when high voltage is applied between cathode and anode, a stream of electrons, these stream of electrons is called as cathode rays, are accelerated from the cathode to the anode. When these are bombarded on the anode, anode produces X-rays, okay, and they are emitted at 90-degree angles to the direction of cathode rays. Now there are other methods, as I said, by exposure of a substance to a primary beam of X-rays to generate secondary beam of X-ray fluorescence. Now please note down the word fluorescence. We are talking about X-ray fluorescence. जैसे UV fluorescence होता है, visible fluorescence होता है, there is X-ray fluorescence. Then by use of radioactive source whose decay process results in X-ray emission. So it is also a secondary process, like the decay process will emit gamma rays. Those gamma rays, when released from nucleus, they bump into the innermost orbitals of the element of the atoms, and that energy is acquired by that electron, and then that electron emits X-ray. Then from synchrotron radiation source. Now this is very costly and very few labs have this facility. In your syllabus, you have only first one to be studied in detail. Now, X-ray diffraction method works on principle of interference. So in X-ray crystallography, we use principle of interference to find the distance between all atoms. We have seen interference pattern before also. Where we have seen interference pattern, in which chapter, where it is? Two types of instrumentation we have seen this interference pattern. Okay, maybe you are not remembering this. First is monochromatous, and second there was FTIR. So in both we have seen interference pattern. So let us see what the general idea is. Atoms in a particular plane will align so as to give a diffraction pattern at a particular angle of incidence for X-ray beam. The reflected beam from each atom acts like the slit in Young's optical diffraction experiment. You must be remembering that double slit experiment. There is a source of electromagnetic radiation, then you have an aperture on the screen, and then you have another screen where there are two holes. So the light coming from electromagnetic radiation over here, okay, here it acts as this first screen, and its aperture acts as the primary source of the light, and it produces these secondary sources. This is your 12th standard experiment. So on the screen which is placed over here, you will get alternate bands of high and low intensity. This high intensity band will be followed by low intensity, again high intensity, and so on. Okay, so alternate bands of high and low intensity, bands of say light and darkness. Okay, so when we say about X-ray crystallography, every crystal is made up of many layers of atoms. So when X-ray passes through it, okay, suppose X-ray is falling and there are many atoms. If you consider only first layer of atoms, that atom will scatter the X-ray, and this will be analogous to this one. Okay, so it will act as secondary source of electromagnetic radiation. I hope you understood this paragraph now. Each atom in selected plane acts as coherent point source, and the wavefronts interfere to provide diffraction pattern. So this is the first layer and this is second layer. So you will get a diffraction pattern. This is called as a diffraction pattern. Because we have coherent sources in 3 dimension, we get an interference pattern consisting of spots instead of line. See, I will explain this part of this paragraph. See, अगर समझो होता ऐसा है कि एक ही सिंगल लेयर होता था atoms का, like here it is only single atom, and then it is single layer of next point sources, secondary point sources. So you got bands, okay, alternate bright and dark bands. But this is not a 2-dimensional when it is a crystal. It is 3-dimensional. So light is not just producing interference on XY plane. It is producing interference on all possible planes. So interference pattern is not alternate bands. Like suppose this is screen, okay, this is the screen, और हम वो screen पे interference pattern देख रहे हैं when it is a planar structure. When it is a planar structure, so what you will observe? You will observe alternate dark bands and bright bands. But if it is not a 2-dimensional structure, if it is a 3-dimensional structure, and this is your screen, so you will observe instead of bands, you will observe patterns which are in the form of points and not bands. Okay. Now, however, the method of finding the distance follows the same general idea as that developed in the previous slide. That means interference pattern के लिए ये जो है bands, the logic behind this and logic behind these dots remains the same. There are some mathematical calculations. If you will follow that, you can exactly predict what is the distance between individual atoms which are producing this pattern. Okay. Now, you don't have to go in that detail how that mathematics is applied and how the pattern is produced. If you remember just this much, that some mathematical calculations are applied by measuring these distances between dots. Okay, these distances between dots is measured, the pattern is studied, and for different pattern there are different formulas. There are only certain number of patterns that are available. That is because there are only certain number of crystals that are possible. That's why, because there are certain number of, say, there are 20 number of crystals possible. So for 20 types of crystals, there will be 20 types of crystal patterns. So looking at the crystal pattern, the analyst will understand which formula is to be applied. So formula is fixed. Now only what is remaining? Measuring distance between these dots. So they will measure the distances between the dots, put those values in the formula, and they will calculate exactly what is the distance between the individual atoms within the crystal. Okay. Now let us understand what are crystals. Let us try to understand 3-dimensional structure of crystals. Acha, do you have any doubt in this particular slide, students? Anybody? I will revise it quickly. By the time अगर आपको कुछ doubt होगा तो पूछो. The gist of this slide is, first part is telling you that interference pattern will be obtained. This interference pattern will be in the form of dots and not bands because crystal is 3-dimensional structure, not 2-dimensional. So you will get patterns in the form of dots. Now, these patterns are fixed in number depending on which crystal types are present. मतलब क्या, अगर क्रिस्टल वो जो डॉट्स का पैटर्न आपको समझ में आ गया, you will understand which type of crystal it is. And if you can measure the distance between dots and put those values in the corresponding mathematical equation, you will get exact distance between the atoms in the crystal lattice. Shall we proceed, students? Is it clear till this point? A typical crystal in 3-dimensional looks something like this. Now what I want you people to observe is, observe only this part of the crystal. Okay, let's try to zoom into this. Okay, these dots are representing atoms. Okay, there are vectors drawn. The distance between these two atoms is labeled as A. Between these two atoms it is B, and between these two atoms it is C. And you will see that the pattern is repeating itself. ABC pattern is repeating itself throughout the structure. Now, please note that none of the angle between AB or AC or BC is 90 degrees. So it is not necessary that in a crystal angle should always be 90. And this cell, okay, this single cell is called as unit cell of the crystal. It is called as unit cell of the crystal. Now, how does this, okay, how does this affect diffraction? When X-rays strike a crystal, each atom acts to scatter rays. It acts as if it is a mirror, okay, as if every atom is mirror. It acts like that, and it will produce scattering. Okay, this scattering or the reflections act like slit in our optical diffraction example, that double slit experiment. Each is a coherent source. When we say coherent source, can you tell me what is coherent source? अभी सर ये 11-12 स्टैंडर्ड का किधर से याद रहेगा ना? What is coherent source? The electromagnetic radiation coming from two sources, if those are in the same phase of the motion, then they will be called as coherent source. So they will act as coherent source. In each repeat of the crystal, that is for every cell of the crystal, okay, in each repeat of the crystal, the distance d of a particular atom acts like a set of slits, like the distance between this layer and this layer. Okay, that distance will act like slit, giving a unique diffraction pattern. Now, crystals come in a limited number of forms. This I have mentioned, that there are only certain types of crystals. Okay, it is fixed number. These can be classified according to the axis of symmetry in each form. So every type of crystal has got a different axis of symmetry. For example, observe this particular crystal. Okay, there is one atom at the center of the cube. Okay, this is a crystal. At the center of it, there is one atom. Okay, so observe that crystal. This crystal has 4 axes along which it can be rotated. So there is one axis from the atom to one corner, then this atom to this corner, and remaining to corner. Acha, you have to imagine in your mind now. Select any one axis. Okay, select any one axis. Suppose this axis I am selecting. Now, about this axis, now I want to imagine the rotation. The crystal is rotating around this axis. The axis is joining this corner to the middle crystal to this corner. It is passing through the crystal structure. Now, if I rotate in, say, clockwise direction, this atom over here will first come over here to give me the same structure. Okay, then ये हो गया one fold. Same structure लाने के लिए मुझे कितना rotation करना पड़ा? This is one rotation. This is not complete rotation, part rotation. So this one. Then if I rotate it again, this corner will go over here backside. Okay, but I will get the same structure, crystal structure. So this is becomes second fold. And again, if I rotate, it will become in the original position. तो ये क्या हो गया? I rotated it thrice to get in the original position. तो अगर 3 बार घुमाना पड़ा, तो उसका मतलब ये जो axis है, okay, it is a 3-fold symmetry axis to get the crystal in the original position while passing through the similar structure. देखो ये एटम जब यहाँ पे आता है, पूरा स्ट्रक्चर, पूरा क्रिस्टल जब घूमेगा, it will be, the structure will be similar to the original one. Then again when it will rotate over here, again it will be similar one. And when again it is rotated third time, it will become the original position, the actual position from which we began. So we have to rotate it 3 times to come in the original position. So it is 3-fold symmetry. Now this 3-fold symmetry is characteristic of a cubical crystal. So it has a cubic symmetry. Now what is this 3-fold symmetry? It means that we rotate the crystal about full 360 along one of these axes. There are 3 points after every 120-degree rotation at which it looks exactly same as the previous one. The bottom crystal, that is this particular crystal, is monolithic it has one axis of two-fold symmetry C2. Okay, it has got that only one axis. मतलब ये जब rotate करेंगे, when this atom over here is rotated over here, it will be a similar structure. Again, it will be rotated over here in the clockwise direction. There will be second structure. Okay, so two-fold symmetry. The crystal forms reflects the dimension of unit cell. I hope you understand this. Now, if you have understood that, this way of representing crystal is expressing the crystal in the form of Bravis lattice. Okay, so unique crystal forms, the 14 Bravis lattices are possible. So only these 14 structures are possible by this method of expressing the crystal structure. Now, in all the structure, you may be observing that there are certain letters mentioned. Either it is P, or it is C, or it is I, or it is F. Okay, so the letter P denotes the primitive unit cell, I indicates a body-centered unit cell, F indicates a face-centered unit cell, and C a unit cell with lattice point on two opposite faces. When we say lattice points, it means the atoms like this. See, this is the face of the crystal. There is one point over here and one point over here. It is on the face. The shaded area are the unit cell where the angles are not 90 degrees. The dotted lines show the equivalent face right angled volume. So it is not necessary that the faces should be at 90 degrees to each other. Now you understand the concept, students. Okay, just understand there are different ways of expressing the crystal structure with Bravis lattice. The details are not required, just understanding the way it is representing, that much is expected at your level. Now, these crystal structures were with respect to points or the atoms of the crystal lattice. There is another way of considering the planes within the crystals. For any repeating two-dimensional lattice, we can draw lines through the points which have various slopes. In 3D lattice, these lines are projected in the third dimension to form planes. Okay, like suppose you observe over here. Okay, if this is a crystal structure, we can draw lines in various manners. Okay, so lines with different slopes. It is the same thing. Observe that these all are the same crystal structures, but we are drawing lines in a different manner. The crystal structure is same. Okay, now imagine we have here seeing only one layer of the entire crystal, the layer which is facing the observer. There will be layers behind this layer also. If you join all those layers, you will get planes instead of lines. Okay, so for a molecular crystal, each atom is in a regular repeating pattern. So we could draw planes through sublattice for each atom. The distance between the planes of different atoms would then tell us the structure of entire lattice. If you can measure the distance between atoms, like here it is, distance between these two atoms is A, these two atoms is B, these two atoms is C. Okay, if you can measure the distance between the planes for different atoms would tell the structure of the lattice and hence the structure of the entire molecule. The general principle of crystallography is to determine the structure by looking at these repeating distance. So the pattern that we will observe after diffraction, we need to find out the distances which are repeating themselves. This is achieved by taking advantage of the diffraction of X-rays or accelerated electrons or neutrons. Okay, X-ray, what is alternate to X-ray? We can also use accelerated electrons or accelerated neutrons, all of which have wavelength in the range approximately 1 angstrom, which is appropriate for molecular bond distance. So the distances of the molecular bonds are of this degree. So these are appropriate for measuring those distances. X-rays are reflected of the electron clouds around the atoms and bonds and form diffraction patterns that depend on angle of X-rays with the planes and on the coincidence between the repeat distance and the wavelength of the X-rays. So depending on the distance and angles between the atoms, a certain pattern is formed. Now, let us see what are Miller indices. We saw that there are ways to present atoms in terms of planes, lines, and every single unit of the crystal is called as cell. So, in a two-dimensional lattice, the planes are represented by parallel lines connecting the points, like over here. Okay, connecting the points. The slope of the line is given by the number of units in the a and b axis. So instead of x and y axis, we have a, b, and c axis. Here we are looking at only a and b axis. Okay, where a and b define the unit cell. In A, if you'll observe over here, this, okay, in A, we have slope defined by 1A and 1B. That is 1 unit of A and 1 unit of B. In B over here, that is over here, the slope is 3A, 2B. Now I will tell you how it is 3A and 2B. Okay, so this is 1A, this is 2A, and this is 3A. This is 1B, and now this is 2B. So this 3A comma 2B is one cell in this case. Okay. Then in case of C, okay, it is minus 1A and 1B. Now why it is minus sign? Let us, instead of starting from here or here, let us start over here. Okay. This is the repeating pattern. So this is A and this is B. But the distance is measured from this to this, so it is in the negative direction. That's why minus 1A and B. And in terms of D, okay, the description lines of lines in D are a little problematic because, see, because they never intercept A axis. Okay, since they are parallel to it, so there is no interception, they are parallel to it. Similarly, if the lines represent planes with the third dimension perpendicular to the AB plane, that means a plane behind this, then all planes will be parallel to the C axis. In principle, we could define the planes in terms of intercept. So for A, it would be 1 comma 1 comma infinity, and for B, it would be 3 comma 2 comma infinity. And hello students, my laptop actually malfunctioned. I'm trying to get back the PPT again. Have some more patience. Okay, so we were on this particular slide. Okay, so these are the different ways of expressing different atoms within the crystal lattice, and we get to know a single unit of the entire cell by indicating the distances in terms of A, B, and C. Okay, now if you will see these A, B, and C, we can have the values assigned of a single unit. In order to avoid infinity term, it is more convenient to take reciprocals of these values. In order to avoid fractional numbers, the results is multiplied through to give the lowest integer set. Now, what we get then are called as Miller indices for the planes. So for every plane, like this is the plane that we are observing, for that plane, this is the single unit. For every atom, we will get one value of the indices called as Miller indices. Now, these are named the H, K, and L values. So distance between these 2 points along the A axis will be named as H value, and here it will be named as K value. Okay, and they are shown in the figure like this. For examples of the plane through different crystal lattices, the planes on the right over here are for the cubic lattices, and some of these are on right or not right angles. These planes are shaded. See, so this 1 1 0, so these are value of HKL. 1 0 0, again these are value of HKL. So for every type of the cube, you have different values of H, K, and L. So now we know how many types of crystal lattices are possible, and how to express every atoms within the crystal lattice. we can now go to the next part of the chapter, Bragg's law. Now, Sir W. H. Bragg and his son, Sir W. L. Bragg, developed a relationship in 1913 to explain why crystals reflect X-ray beams at certain angles of incidence, that is theta. Okay, so they are trying to correlate the structure of crystal with this angle theta. Okay, in 1915, the father and son were awarded Nobel Prize for Physics for their services in the analysis of crystal structure by means of X-ray. When a beam of X-ray strikes crystal surface at some angle theta, portion is scattered by the layer of atom at the surface. Like, suppose this is the crystal, okay, and this is the incident angle, and it is striking one atom at an angle theta. Okay, after hitting this atom, the ray will get scattered. The unscattered portion of the beam penetrates the second layer of the atom, where again a fraction is scattered and the remainder passes to the third layer. See, this ray has hit this particular atom, but the adjacent ray has not hit any atom. The adjacent ray has penetrated the first layer and went into second layer and hit over here. There is another layer which did not bounced on atom in the first layer. It penetrated second layer and then it bounced off the third layer. Okay. So the third point, the cumulative effect of the scattering from regularly spaced centered of the crystal is diffraction of the beam in much the same way as visible radiation diffraction by reflecting grating. Now, what we are talking here is, see, you can see over here that beam has reached over here, then it is bounced off from here. Then second ray is bouncing off from here. Third ray bouncing off from here. Now, this over here is formation of a new front, new wave front. Now, all the rays have traveled different distance, so there will be phase difference between the rays in this solvent front. The problem or the advantage is this is happening through layers which are equally spaced. So this is happening via a layer of crystals which are placed via equal distance. So there is a new wave front forming here. So these waves may or may not be in the same phase. So if they are in the same phase, constructive interference will be forming. If they are in different phase, destructive interference will be forming. So the requirement for X-ray diffraction are, first, the space between layers of atom must be roughly the same as the wavelength of the radiation. It means whatever is the wavelength of these waves, okay, the distance between the layers should be approximately equal to, I am not saying exactly equal to, approximately equal to those rays. The scattering centers must be spatially distributed in a highly regular manner. That means it should be a crystalline structure. Now, क्या बात है? Sajil Mullah is asking permission to join the lecture. Okay. Okay, so let us derive the Bragg's law. Okay, here a narrow beam of radiation strikes the crystal surface through an angle theta. Okay, this is the angle theta. Scattering occurs as a consequence of interaction of the radiation with atoms located at O and located at P. Okay, and located at R. So OPR. We are considering only these three atoms and scattering occurring at these three atoms. Now, if the distance AP, that is distance from this point to this point, now you must be wondering what are these A, B and CD points. So what they have done is, from the position of atom O, they have drawn perpendiculars on the beams which are penetrating second and third layer. So this OAB line, this particular line, represent a wave front. Now at this particular wave front, all these three waves are in the same phase. Okay, they are in the same phase. Similarly, from this point O, they have drawn a perpendicular on the a wave that is bounced off from P and R. So me clarify that. These are perpendicular. This is 90-degree angle. Okay. Now, if the distance AP, that is distance from this point to this point, plus distance PC, that is distance from P to distance to C. If this addition of distance is equal to n lambda, then there will be constructive interference. इसका मतलब क्या है? See, the wave is in one particular phase at this point, okay, which is similar to wave over here, okay. If the wave is traveling this much of distance, and if it is in the same phase, it should travel a distance which is integer multiple of the wavelength itself. Then only these two waves will be forming the constructive interference. That's why this equation AP plus PC is n lambda. Now, where n is the integer, the scattered radiation will be in phase at OCD. अगर वो condition fulfill होता है, then only there will be constructive interference at OC. Similarly, if BR plus RD is equal to m lambda, there will be constructive interference throughout at OCD wavefront. Okay, and if that happens, the crystal will appear to reflect X-ray radiation. Only in that case, it will appear that crystal is reflecting the X-ray radiation. Suppose ऐसे होता है कि there is no constructive interference, there is destructive interference. Suppose there is destructive interference. In that case, there will be no shining of the crystal, because these waves will be in the different phase. They will cancel out each other and crystal will remain dark. Okay, I hope you are getting the point, students. Only when there is constructive interference of the X-rays which are bouncing from the atoms, then only you will get a point on the screen. At all other distances, you will get a dark spot, okay, dark band. Now consider this triangle. So the triangle, if I have to draw, can draw like something like this. And this is angle theta. Now, the distance between two layers of the atom is small d. So OP is small d. So here it is small d over here. Now, if this is the case, okay, हमको क्या करना है? Constructive interference देखना है. Okay, so we know theta, we know distance d. So how will we express distance AP? How to express that distance AP? Okay, now in this case, what is sine theta? In this case, sine theta will be AP divided by OP. So AP will be OP multiplied by sine theta. But OP is nothing but D. So AP is equal to D into sine theta. I hope you understood it. AP is equal to D sine theta. Similarly, we can prove for PC. For PC also, we can prove that it is nothing but D sine theta. Okay. But we have a formula over here. We have this equation over here. N lambda is equal to AP plus PC. But both have the same value, that is D sine theta. So if you can combine these two equations, you will get N lambda is equal to 2D sine theta, where D is the interplanar distance of the crystals. Thus, we may write that the conditions for constructive interference for the beam at right angle theta is N lambda is equal to 2D sine theta. Now, this equation is called as Bragg's law. This equation is called as Bragg's law. This is one of the easiest derivation. Bragg's law is of fundamental importance. सबका नेट पैक खत्म हो गया क्या? Everybody is asking permission to join the lecture. I will extend for 5 more minutes, then we will stop. Maybe remaining chapter we'll see it next time. Note that X-ray appear to be reflected from the crystal only if the angle of coincidence satisfies the condition. At all other angles, destructive interference occurs. So only when the theta value is just right, we will get the crystal reflecting the. So see, This is the modern automated X-ray diffraction. यहाँ पे sample रखते हैं. Sample will be placed over here. From here, you will get bombardment of X-rays, and here you have detector. The detector can be rotated. Okay, detector can be rotated like this also. And it can be rotated from this angle also. So in all three dimension, it can rotate, and it will pick up the spots where you have got the crystal which is shining. So all those angles will be multiple of angle theta for that phase of the crystal. I think we should stop here. The remaining part we will see in the next lecture.